In our last lecture on causal inference, we looked at the selection on observables framework, which I'm just going to summarize quickly on this slide to refresh your memory. We had a binary treatment, and we had two potential outcomes, y0 and y1. We had an observed outcome y that was equal to y0 if you are untreated, and equal to y1 if you're treated. And then we had these two assumptions. So we assumed, first of all, that D is independent of the potential outcomes, conditional on observed covariance X. That is called the selection on observables assumption. And then we also assumed overlap. In other words, we assumed that the share of people who are treated among people with a particular level of the covariate variables X is always strictly between 0 and 1. And in this context, there are a number of different ways that we can carry out meaningful causal inference using observational data. We talked about regression adjustment. We talked about propensity score weighting. We didn't talk about matching, but that's an alternative. What we have ignored so far is the question of what we should include in X. We just kind of leapt to this assumption, selection on observables, that says that we know which covariates we need to adjust for. But that just raises the question, how do you know in practice what variables you should put into X? You might think that the answer is, let's just throw the kitchen sink at the problem, put in as many X's as we can find. But what I hope to show you today is that that's a really bad plan. So as a warm-up, let me remind you of the familiar omitted variables bias formula that you may have encountered among other places in the book Mostly Harmless Econometrics. So let's keep things really simple. I'm going to assume a linear causal model with homogeneous effects. So everyone has exactly the same treatment effect. The model is linear. Y equals alpha plus beta D plus gamma X plus U, where both D and X are exogenous. They're uncorrelated with U, and U is mean 0. So if we want to convert this to the potential outcomes framework, it's fairly straightforward. Y0 is your potential outcome when you're untreated. To obtain this, we set D equal to 0, which gives us Y0 is alpha plus gamma X plus U. And in this case, y1 is going to be exactly the same thing as y0, but with that added increment of beta, because y1 is what you get when you set d equal to 1. So in this particular example, everyone has exactly the same treatment effect. y1 minus y0 is just beta. So beta is the ATE, and beta is also the TOT. All right, so what would a regression of y on d identify? This is often called the short regression because it excludes this x variable. Well, in the population, the regression slope is going to be equal to the covariance between d and y divided by the variance of d. And if we just substitute in our expression for y, namely the causal model, we're going to get covariance of d with alpha plus beta d plus gamma x plus u divided by the variance of d. So then we can use our favorite properties of covariance to simplify that expression, along with the fact that d was, by assumption, uncorrelated with u. So remember, we had this linear causal model, and in that causal model, d and u were exogenous. So that's going to leave us with beta plus gamma times covariance dx divided by variance x. So what this tells us is that the short regression coefficient will only be equal to beta, which was our treatment effect of interest, if gamma is 0, in other words, x doesn't matter for y, or if there is no covariance between d and x. So you sometimes hear that omitted variables bias formula interpreted to mean that we should adjust for any observed variable that is correlated with d and y. They don't say that in Mostly Harmless Econometrics, but it's something that you certainly encounter in some other sources. So that's actually wrong, and I want to take a moment to try to explain why. What the omitted variables bias formula tells us is when and how the coefficient on d will differ depending on whether we include x in the regression. And in fact, the algebra holds regardless of whether any of this stuff is causal. So if you go back to that previous slide and you cross out everything I said about causality, you just interpret the long regression as a population linear regression model, then everything still goes through. So the short regression only includes d, the long includes both d and x, and we're just checking when the short and long coefficients agree. They agree if and only if y does not help to predict y in the long regression, or x is uncorrelated with d. That doesn't necessarily have any causal content at all. It obtains some causal content only if we assume that the long regression is the true causal model. So let me say that again. This argument only tells us something about why excluding x could be bad if we assume that the long regression is the true causal model. If that's the case, then indeed we know when it would be bad to drop a particular x. But what this does not tell us is if we don't already know what the right causal model is, it doesn't tell us which x's we need to add. Now, to drive this point home, I'm now going to show you a simulation example where I have an x that is correlated with d and also with y. This x matters for both of them, but it would be a terrible idea to include it in your selection on observables estimation procedure. So on the left-hand side, I'm going to generate the data, and on the right-hand side, I am going to use the regression that we talked about in our last lecture to actually carry out selection on observables, and I'm going to do that selection on observables adjusting for x. The spoiler alert is that it's going to turn out that adjusting for x is wrong. It gives us the wrong answer. So let's see why and how. I'm going to start off by generating a binary d. So d is a vector of length 5,000, and inside that vector I have 5,000 independent and identically distributed Bernoulli random variables with probability of success 0.4. So that's how I generate d. I generate x using the observed values of d. So I generate x conditional on d. X is also binary in this example to keep it nice and simple. So x is a vector of length 5,000 containing Bernoulli draws, and the probability of success for each element of x actually depends on the corresponding element of d. So when d is 0, the probability of success is 0.25, but when d is 1, it's equal to 0.25 plus 0.5, which is 0.75. All right, now I'm going to generate y. So y is equal to x plus some standard normal random noise. Okay, so what I'm now going to do is I'm now going to show you a number of calculations using this particular model, using this particular causal model. And it is a causal model because on the computer, if I were to change any of the values, if I were to change a value of d or x, I would causally affect the outcome y. So this is a causal model, and it has a very particular structure. The way that this causal model works is that d causes x, and x causes y. So you might ask, well, how come d causes y if the equation for y does not include d? You're right that the equation for y does not include d, but if I changed the value of d, that would have an effect on x, because remember that the probability of success for x depends on d, and that effect would carry through to y. Okay, so now I'm going to carry out a number of calculations. The first calculation, which is on the bottom left-hand column, right at the bottom of the code block, is I'm going to compute the naive difference of means, y when d is 1, compared to y when d is 0. Now that naive difference of means is 0.52 approximately. Now let's look at the right-hand side column, which has another block of our code. So I'm just going to load a few libraries here, and now I'm going to carry out exactly the steps that we looked at last time when we saw how to use regression adjustment in practice if you had binary treatment and one or more binary covariates. So here I have a single binary covariate x. I'm interested in the causal effect of d on y, remember, and I'm going to adjust for x. So I will run this regression. The regression is of y on d, x, and then the interaction between d and x that has been had its mean subtracted from it. So I call that demeaned value of x, I call it x tilde. All right, so what do we get when I run the regression? Well, we get an estimate of approximately 0, so 0.01, and we have a standard error of 0.03. So if you wanted to build an approximate 95% confidence interval here, you would say, yeah, that's sort of statistically indistinguishable from 0. So, okay, which of these is right? 0.52, which is the naive difference of means, or 0, which is what we got when we did regression adjustment adjusting for x? Well, to answer this question, let's take a look at the potential outcomes. So the average treatment effect is the expected value of y1 minus y0. Okay, so now what is this? Well, let's trace this logic back. So what is the expected value of y1 minus y0? Well, I'm claiming here that it's actually equal to the expected value of y conditional on d is 1 minus the expected value of y conditional on d is 0. Now, why is that? Well, again, that's because I generated the data from this very particular causal model. I generated the data from a causal model where I know that d actually does cause y. So just take a look at the left-hand side of the slide. D causes x and x causes y. So there is clearly a causal effect of d on y. It goes through x because x has a distribution that depends on d, but changing d definitely does probabilistically change y. So actually, it's perfectly valid, given the way that I set up this simulation, it's perfectly valid for me to compute the naive difference of means, y given d is 1 minus y given d is 0. All right, and so what is that equal to? Well, the expected value of y given d is 0. Remember what y actually is. Y is x plus random normal noise. So that means that's the same thing as the expected value of x given that d is 1 minus the expected value of x given that d is 0. And that is 0.5, because we can see in the expression where I generated x that increasing d from 0 to 1 has the causal effect on a probabilistic level of taking x from having a mean of 0.25 to a mean of 0.75. And that is exactly what flows through to y. So I'll repeat that because it's very important. Changing d from 0 to 1. So that's the intervention we're imagining doing. Changing d from 0 to 1 will have the following effect on y. First, it changes the average level of x from 0.25 to 0.75. That's because x has a distribution that depends on d. And that, in turn, changes the average value of y. It changes it from 0.25 to 0.75, because y is simply x plus random normal noise. So that means the causal effect of d on y really is just 0.5. But when we did our regression adjustment on the right-hand side, and we adjusted for x, x is a variable that is correlated with d, and it is a variable that definitely matters for y, that somehow gave us a very wrong answer. So what's happened here? Well, x is a prototypical bad control. It is what is called an intermediate outcome. In other words, x is itself an outcome of the treatment d, and it's an outcome that goes on to cause y. So adjusting for an intermediate outcome has the effect of masking the causal impact of the treatment on that outcome. I'm going to give you an example. So suppose that a randomized early childhood intervention causes people to be more likely to attend college, and that attending college makes you more likely to earn a high wage. Well, in that case, we don't want to adjust for whether you attended college or not when we're trying to determine the causal effect of the childhood intervention on wage. The right thing to do is simply to do the naive comparison of means between the children who were randomly assigned to the treatment and the children who are randomly assigned to the control. So in our simulation, we have a very, very, very stark version of an intermediate outcome, because in the simulation, 100% of the effect of d on y operates through the effect of d on x. Right, so clearly the first bad piece of advice that I showed you is really, really bad, just as I claimed. So here's some other common advice. And I took this piece of advice from section 3.2.3 of Mostly Harmless Econometrics, but you can find similar statements elsewhere. Variables measured before the variable of interest, d, was determined are usually good controls. In particular, because these variables were determined before the variable of interest, they cannot themselves be outcomes in the causal nexus. So this statement, it has something useful in it. It's true that if we have things that were measured before d, then they can't be causes. I should say they can't be caused by d. If we measure something in the past, d shouldn't be able to cause it. Well, There's still a problem, though, and the problem is that this advice, too, doesn't quite handle all the situations that we're going to run into. So let me now show you an example of a variable that is determined before the treatment. So it's determined before D, but it's actually a bad control. It's one that if we control for it, it's going to make things worse. Okay, so here is a bad control that is not an intermediate outcome. So here is an x that if you adjust for it, it's going to take you from having, it's going to give you the wrong answer to your causal inference question, but it's not itself an intermediate outcome. So it's not an outcome of the treatment. Okay, this one's going to be a little bit more involved. So on the left-hand side, I am using a command that you may not have seen yet, although when we talk about instrumental variables, you will see this command because, well, actually, you'll see it before then. You'll see it when we talk about the multivariate normal distribution. So this is a command that can generate correlated normal draws. So on the left-hand side, what I'm doing is I'm setting up a correlation matrix. I'm then going to use it to simulate some errors, u and v, that are correlated with each other. They're normally distributed, and they each have variance 1, but their correlation is 0.5. So you can just skip right down to the line where I set up x if you like, and you can just remember that u and v are standard normal errors. They're a vector of standard normal errors, and they are correlated with each other with correlation 0.5. All right, so I'm going to generate x as a random coin flip. So here it is. X is going to be a sequence of Bernoulli random variables with probability of success 0.5. And now I'm going to generate d as follows. So d is a little indicator variable, so it's 0 or 1. And whether d is 0 or 1 depends on the value of x and also the value of v. So this is a little threshold crossing model. This is actually a little probit model, little probit regression model, if you're familiar with that, which is something that presumably you have seen in introductory econometrics. So what do we end up with here? Well, we're finally going to have y. So y is equal to minus 0.3 plus d plus u. And remember that u and v are correlated. Okay, so again, if we take the naive difference of means here, we're going to have the mean of y, given that d is 1, minus the mean of y, given that d is 0. If we take that difference, we get about 1.5. Now, that's the wrong answer. I should point out straight away. That's the wrong answer because if we take a look at the causal model, what we can see is that changing y, changing d, intervening to change d, would have its impact in the final line of code, y gets minus 0.3 plus d plus u. So changing d from 0 to 1 actually has a causal effect on y of 1. I'll say that one more time. If you look at the equation for y, the equation that actually generates y causally on the computer, changing d from 0 to 1, intervening to change the value of d in that equation, would change y by 1 unit. Changing d from 0 to 1 has exactly the same effect on y. It increases it by 1 unit. So clearly this naive comparison of means is wrong. 1.5 is not the right answer. All right, so you might think that's fine. We're going to try to do selection on observables here. We've got an x. Let's try to adjust for this x, because this x is not an intermediate outcome. It is something that is determined before d is determined. We can see that right in the code on the left-hand side of the slide. X comes first, followed by d. All right, so let's try to do our regression adjustment. Same exact code as on the last example. So we're going to use regression adjustment by regressing y on d, x, and the interaction between d and a demeaned version of x. So here's our estimate. Here's our standard error, 1.9. Nice tight standard error, about 0.04. So this one is even worse. So the first answer, the naive comparison of means, that was wrong. We know the true causal effect should be 1. Then we thought we'll adjust for this x because it's not an intermediate outcome, but that just made things even worse. So what's going on here? Well, In this example, x is a valid instrumental variable for the endogenous treatment D. But this is the wrong way to use an instrumental variable. The right way to use an instrumental variable is not to plug it in as a control, it's to run IV. And what's actually happening here is kind of subtle, it's very interesting. Adjusting for this x, which as I said is a valid instrument, actually soaks up the exogenous component of D. And that has the effect of making the bias worse than it otherwise would have been. We saw that's exactly what happened in the example on the previous slide. Whereas if we run IV using the ivreg command, and I should, by the way, point out that on this slide, I'm using the library AER to run IV regression in R. But these days, it's actually better just to install the package ivreg. It implements exactly the same command, but it's kind of like the successor to this AER package that only focuses on instrumental variables regression. So AER still exists, but I would actually recommend using the ivreg package to access the same command, so you make sure you have the most up-to-date version. But it's not going to matter for this example, and as we can see, if we were to actually run IV, so run an IV regression of y on D, using x as the instrument, everything would work out right. We would actually get precisely the right answer in this case of 1. So where are we? I've given you a few suggestions for how we might decide which variables to include in x, and none of them seems to have worked. Well, are you feeling confused? Is this just a matter of I know a good control when I see it? First, the bad news. The bad news is that meaningful causal inference always requires assumptions, and that is even true in randomized controlled trials. If you don't agree, I'm very happy for you to fight me in the comments, but meaningful causal inference always requires assumptions. Causal inference from observational data requires even more assumptions than causal inference in randomized controlled trials. So causality is important. Randomized controlled trials have all sorts of exciting advantages, but yeah, meaningful causal inference is hard. And because we're looking at observational data now, our life is particularly hard. Well, should we just give up? Perhaps we could give up if we like, but there's a better way, and that is to try to write down our assumptions. So if you are willing to make your assumptions explicit, then there is a definitive solution to the question of whether something is a good control or not. So if it is possible to use selection on observables, and you've written down all your assumptions explicitly, it is possible to find out what the correct set of x variables to adjust for is. If it's not possible, it's also we can also show why that's the case. And as a free bonus, we're going to get some better intuition about bad controls. The title of this slide, I should say, comes from philosopher of science Nancy Cartwright, who said, "No causes in, no causes out." And that's a great way of putting my bad news from this slide. So, to help understand the framework that I am about to introduce, I would like to give you another example. This is sometimes called the birth weight paradox. It's appeared in a number of different papers in the epidemiology literature, and at the bottom of the slide I have a link to one in particular from which I took this quote. This refers to a paper that indicated that among low birth weight infants of less than 2,500 grams, maternal smoking was associated with lower infant mortality. So the babies whose moms smoked were less likely to die. The results have been replicated in a number of studies and populations, and these seemingly paradoxical associations are now often referred to as the birth weight paradox. So let me give you a stylized version of this example on the right-hand side of the slide. Let's let D equal 1 if a mother smokes while pregnant. Let's let Y equals 1 if the infant dies, and let's define X to be 1 if the infant is low birth weight. So here is the question. Here is the causal question. We want to know the causal effect of smoking on infant mortality, and in order to learn this effect, should we adjust for low birth weight? So to learn the causal effect of D on Y, should we adjust for X? And we're going to return to this question at the end of the lecture after we've developed some tools that will allow us to answer it. All right, now we're going to change gears completely, and we're going to start talking about graph theory. So don't worry, if you've never encountered graph theory before, I'm going to start completely from scratch, and the tools that we will need are very, 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 very simple, just a handful of definitions and some very simple properties. So, what is a graph? Well, it's a set of nodes connected by edges. So on the right-hand side of the slide, I have depicted some nodes. Those are the little circles that have labels on them, like X, D, Z, Y. And these nodes are connected by edges. Those are the lines, and in this particular example, my lines have arrows on them, although some graphs don't have arrows on them. Two nodes are said to be adjacent if they are connected by an edge. Edges can be directed, as they are in the figure at right. That means they've got an arrow showing which way they point, or they can be undirected. That would mean if you got rid of those arrowheads. A directed edge is said to point from a parent node to a child node. So then in this example, Z is a parent of X. There's a directed arrow. There's a directed edge from Z to X. A directed graph is a graph that only has directed edges. A path is a sequence of connected vertices, and a directed path is a path that obeys one-way signs. So what do I mean by that? Well, in the graph at right, there is a path between, let's say, between D and Z that goes D to Y, Y to Z. That's a path because D is connected to Y and Y is connected to Z. But the path from D to Y and Y to Z is not a directed path because it disobeys a one-way sign. So D to Y has an arrow pointing along the path from D into Y, but Y to Z doesn't. For Y to Z, the arrow is going the wrong way. So overall, that is not a directed path. A directed path is said to point from an ancestor to a descendant. So X is an ancestor of Y in this particular graph through D. And a cycle is a directed path that returns to its starting node. So if you walk along this graph and you follow all the one-way signs and you end up exactly the same place where you started off, that means that you return to your starting node. You have traversed a cycle. An acyclic graph is a graph that doesn't have any cycles. All right, so now I would like you to test out your understanding of this terminology. So you can pause the video and try to answer the following exercise. Is this a directed graph? Is it acyclic? Are Z and D adjacent? Can you list all the paths between D and Y? And can you list all the directed paths from D to Y? All right, this is definitely a directed graph because all of the edges have arrows on them, so they're all directed. Is it acyclic? Yes. If you walk along this graph, no matter where you start, you can never come back to the same place. Go ahead and give it a try. See if there's some way to go from X back to X, and the answer is no. You can try that for each of the nodes, D, Z, and Y. It's not going to work. All right, Z and D, are they adjacent? Well, no, because there is no edge between them. What about all the paths between D and Y? Well, there are actually 3, and I've listed them here, but only one of those paths is directed. We're now going to get back to causality after our brief introduction to some terminology from graph theory. So graphical causal models rely on what are called directed acyclic graphs, or DAGs for short. So you already know what it means for a graph to be directed, and you already know what it means to be acyclic. A directed acyclic graph is simply both of those things at once. So a graphical causal model, which relies on a DAG, contains directed edges that encode assumptions about the flow of causation. So the presence of a directed edge shows that causation flows from one thing to another. The lack of such an edge denotes some sort of lack of causation. If D is an ancestor of Y, we say that it is a potential cause of Y. If D is a parent of Y, we say that it is a direct cause of Y. And remember the distinction between ancestor and parent. It's exactly the same one that you would use in your own family. So your grandmother is your ancestor, but not your parent. Your mother is both your parent and your ancestor. So a direct cause is about having an arrow pointing from one thing directly into the next thing. So we're going to be spending a lot of time in the remainder of this lecture talking about what is called the backdoor criterion. And the backdoor criterion is about whether we can learn the causal effect of our treatment D on some outcome Y using selection on observables. If we can learn it, then which covariates should we adjust for? I mentioned before that this lecture is going to be about saying what you assume to be true and finding out what that implies. So we've got to draw our assumptions. I think I stole that quote from Richard McElreath. I should probably check that. But if you haven't watched his amazing set of lectures on statistical rethinking, I highly recommend them. He also talks about DAGs a little bit differently than I do, but his lectures are amazing, so you should certainly check them out. All right, so back to this birth weight example. I am going to define some variables here. So Y is mortality, X is birth weight, D is maternal smoking, and U is going to be other stuff. So U stands for unobserved. And what I mean when I write U down is that I don't believe that D and X, namely birth weight and maternal smoking, are the only causes of infant mortality. There's a lot of other things that could happen that aren't those two things that could have an impact on whether an infant survives. Okay, so the question here, if we take a look on the right-hand side, is suppose that we think this is a possible model for the birth weight example. So let's talk our way through this DAG on the right-hand side. Remember that the directed edges, those arrows, they describe the flow of causality. So what I'm saying here is I think there could be some unobserved things, maybe they include things like malnutrition or a birth defect or various other things. Those unobserved things might cause X, but also cause Y. So like malnutrition could cause birth weight to be lower, and malnutrition could perhaps cause infant mortality. So U causes both X and Y. I've also drawn an arrow from X to Y. It seems quite plausible that birth weight can have a causal effect on mortality. And then I've also drawn two arrows from D to X and from D to Y. So what I'm saying here is I think maternal smoking might actually cause birth weight. So maybe if the mother smokes, that might have a causal effect on the birth weight of the baby. But certainly maternal smoking could have a causal effect on Y. So I have drawn these arrows, and I'm interested in trying to understand whether there is in fact an arrow from D directly to Y. That's the causal effect of interest. And these other pathways are things that I think might be present, other causal channels that could be operating here. So we can't adjust for U. I'm going to assume that U contains all the things that we don't observe that cause X and Y. So the question now becomes, should we adjust for X, birth weight, when we're trying to learn the smoking on mortality causal effect, the D on Y causal effect? And we're going to answer that question by taking this DAG at right as our causal model, because it already embeds some causal structure about where there are arrows and where there are not arrows. All right, now we're going to need a little bit more terminology. So let's talk about causal paths and backdoor paths. A causal path is a directed path between treatment and outcome. it always begins with an edge pointing out of the treatment. So it always begins with an arrow pointing out of D. Okay. A backdoor path is a non-causal path. So that means that it's not a directed path between treatment and outcome. So it's a non-causal path between the treatment and outcome. So it's a path, but not directed. A backdoor path always starts with an edge pointing into treatment. So remember, the causal path is going to go with the flow. It starts at D, it follows the one-way signs, and it flows into Y. A backdoor path does not go with the flow in the sense that it always begins by going against the flow and following an arrow from D back to something else that points the wrong way. So to help you understand this concept, take a moment to pause the video, have a look at the DAG on the right-hand side of the slide, and try to list all the causal paths from D to Y, along with all the backdoor paths from D, backdoor paths between D and Y. Now, in this particular example, there is only one causal path from D to Y. That doesn't have to be the case. There can be DAGs where there are multiple causal paths from D to Y. The way that could happen is, you might have an arrow from D directly to Y, but then you might have an arrow from D into some other variable W, and from W into Y. It's totally possible to have that, but the example here doesn't. What about the non-causal paths? Well, I count two. So we have this path between D and X and Y. And notice that this backdoor path begins by following an arrow that points the wrong way. So there's an arrow pointing from X into D, but we follow it the other way to get to Y. Similarly, there's a path between D and X and Z and Y. And again, remember that the backdoor paths, they always begin by following an edge that points into the treatment. It's time for some surgery. So we're going to cut up this graph and see what we end up with. Let me introduce some more terminology. I know that this lecture is full of terminology, but the thing about DAGs is that they're a very powerful tool. They're not very complicated, but they do require you to learn some new terms. So we're closing in, don't worry, we're closing in on the new terminology that we're going to need. So the first thing I'm going to define is what I will call the observational distribution. By the way, when I say I will call it, that's what it's called. This is terminology due to Perl. So the observational distribution is the actual distribution of Y among people who we observe to have D equal to little d. So this is just literally the same thing as the distribution of Y given D in some population of interest. So this is, in some sense, the observational distribution is just another name for what we would just call the distribution of Y given D. What a DAG shows is it actually shows the observational distribution and the way that it arises from our causal model. There is another distribution, however, and this one is new. This one uses what is called the do operator. This is called the interventional distribution. This is the distribution of Y that we would obtain, notice the counterfactual, if we could intervene and set D equal to little d for everyone. How do we get the interventional distribution? Well, we perform surgery on our DAG. We obtain it by removing the edges pointing into D. So I'm going to say that again because it's kind of the crux of the matter. The observational distribution is the thing that the DAG actually encodes. It shows how our causal model gives rise to all the dependencies between all the different variables. And in particular, it's going to imply a distribution of Y given D. The interventional distribution, on the other hand, is what we get if we go to that DAG and we remove, so we cut out any edges pointing into D. That's going to give us a new DAG. And this new DAG is going to imply how we can see what would happen to Y if we intervened and set D equal to some particular value for everybody. To obtain the causal interest, to obtain the causal effect of interest, we take a look at the path from D to Y in this modified graph. So in particular, the ATE, which, as we know from our previous lecture, was defined as the expected value of y1 minus y0, in this new sort of DAG way of looking at the world, that thing is equal to the expected value of y given do d equals 1 minus the expected value of y given do d equals 0. And if you think about this, it's actually not as strange as it may sound at first. Because what does an experiment do? What does a randomized controlled trial do? Well, it removes all of the existing causes of the treatment. So if we randomly assign some people to go to Oxford University and others not to, that would cut out from the causal model of the world all the various things that otherwise would cause some people to go to university and others not to, because we are intervening and randomly changing whether someone goes to Oxford or not. So what this interventional distribution does is it's sort of a thought experiment. What would happen if we instead had a DAG for an experimental intervention? And that DAG is obtained by cutting some edges out. Here's an example. So on the left-hand side, we have the observational distribution. And on the right-hand side, I am going to cut out all of the arrows pointing into D. There's only one of them. It's gone. And now I've got the do D interventional distribution. The key thing to notice about this interventional DAG is that it has no backdoor paths. Remember that every backdoor path begins with an arrow pointing into D. But I've just removed all of the arrows that point into D. There's none left. That means there's no way for me to form a backdoor path. So it sounds great to cut out all of these backdoor paths, and as I mentioned, that's exactly what a randomized controlled trial would do. I think it might actually be worth pointing it out in the context of this specific example. If we randomly assigned D, we would have the DAG on the right. I'm not sure what Z and X are. This is an abstract example, but it's perfectly possible that there are some causes out there in the world, Z, that causes Y and causes some other thing X, and X that causes Y. Say Y is wage. It's perfectly possible that there's some causal nexus out there between, I don't know, family background Z and wage. Family background can also cause X. Maybe X is, it could be secondary school performance, and perhaps secondary school performance also affects wage. But if we did a randomized controlled trial and randomly sent some people to Oxford, we would still have a nice clean causal path from D to Y. But in reality, of course, the whole reason we're talking about these DAGs is because we often can't carry out randomized controlled trials. So randomization may not be practical, it may not be ethical. So what we're going to do instead is we're going to try to find a way to block the backdoor paths by conditioning. So if we can't cut them out, we're going to try to block them instead. But before we do that, I would like you to now draw the DAG for the do X interventional distribution. A moment ago, we drew the DAG for the do D interventional distribution, but there's nothing special about D. These are just labels. You could do exactly the same thing for X, and I would like you to give that a try now. All right, so in this case, all we've got to do is remove the one backdoor, remove the one edge pointing into X, and there it is. So on the right-hand side, we have the do X interventional distribution. And a few slides back, I mentioned that it's perfectly possible to have more than one path from X, from a treatment to the outcome. This interventional distribution on the right definitely has that. You can see that X has a direct causal effect on Y, and it also has a causal effect on Y that operates through D. We are now ready to begin blocking backdoor paths. And to do it, we need to understand 4 very simple DAGs that form as the building blocks of all of the other DAGs that we could encounter. So this slide shows those 4 DAGs. From top left, I'm going to begin there. We have the fork. In the top right, we have the pipe. In the bottom left, we have the collider. And in the bottom right, we have the descendant. Each of these DAGs has a special lesson to teach us, and once we learn that lesson, we're going to be able to put them all together to solve the problem that we started out with in this lecture, which was the birth weight paradox. We'll start with the fork. The fork is a common cause, also known as a confounder. A confounder is a good control. A confounder is a thing that you would love to adjust for. So the way that this works is, let's suppose that D and Y, let's suppose that we have the DAG at right, which is the fork, okay? So X is a confounder. It is a common cause of D and Y. Now, D and Y are dependent, statistically dependent, because there is an open path between them. There's a path from D to Y because there is a series, a sequence, I should say, of edges that connect D to Y, D through X to Y. But if you look at the DAG, D does not cause Y. In fact, X causes D, and X also causes Y. We can tell that because there is no arrow from D to Y. There's no causal path. Let me say that more precisely. There is no causal path from D to Y. There's no direct arrow that goes from D to Y, and there's no sequence of directed edges that I can follow from D to Y. So in this DAG, conditioning on X actually blocks the path from D to Y. Here's an example. Suppose D is shoe size, Y is reading ability, and X is age. Well, shoe size is correlated with reading ability. Why? Well, that's because younger people have smaller feet, and they haven't yet learned to read. But that's not because shoe size causes reading ability. It's because age causes both. And in that case, adjusting for age would be a good thing to do. So here is the rule that you need to learn when you encounter a fork. When you see a DAG that looks like this, where X is a common cause of D and Y, and there is only one path between D and Y, then D is independent of Y given X. Let me say that just one more time. If X is a common cause of D and Y, and there is only one path between D and Y, then D is independent of Y given X. That's exactly what we've got on the right-hand side of the slide. And this picture actually corresponds to the initial piece of advice that we talked about, a piece of advice that wasn't quite sufficient. But the fact that it wasn't sufficient doesn't mean that it's irrelevant. We talked about this idea of conditioning on things that cause both D and Y, and here it is. The next of these basic DAGs that we need to understand is called the mediator. The mediator is a bad control. You can see the DAG on the right-hand side. D causes X, and X causes Y. This was the example that we saw earlier in the lecture. So in this picture, D and Y are dependent because there is an open path between them. D indeed causes Y through its causal effect on X. But conditioning on X blocks the path from D to Y. So conditioning on this X variable here actually blocks the flow of causation between D and Y. So here's an example. Let's suppose that D is SAT coaching, so coaching on a college entrance exam. X is SAT score, and Y is whether or not you get into college. Well, probably there is an effect, maybe there is an effect, I guess I should say, of coaching on SAT score. There's definitely an effect of SAT score on college acceptance, but if we conditioned on SAT score when we're trying to estimate the effect of coaching on college acceptance, that wouldn't make any sense, because presumably all, or maybe only most, but in this picture, all of the causal effect on college acceptance through caused by SAT coaching would have to flow through SAT score. So now we have the rule that we need to learn for a pipe. If there is only one directed path from D to Y, and X intercepts that path, then D is independent of Y given X. So what this tells us, this is sort of the opposite of the lesson that we got from the previous slide, although it sounds similar. In this case, we don't want to condition on x. So x is an intermediate outcome, and conditioning on an intermediate outcome is a bad idea. In fact, d and y are not independent, but conditioning on x is going to make them become independent. The third special DAG that we need to learn is called the collider. This is probably the most exotic one. A collider is a common effect, and a common effect is another example of a bad control, something we don't want to adjust for. So in this picture, d and y are actually independent. D and y are actually independent. So there is a blocked path between them. This maybe takes a bit of explaining. So the figure at the right has an arrow from d going into x and y going into x. So you see that the two arrows, in some sense, collide at x. In this kind of a DAG, the path is actually blocked. It starts off closed. D and y both cause x, but actually neither causes the other. So in this picture, d and y are independent. If, however, you condition on x, then you're going to unblock the path between d and y. So you're going to create dependence. There's an example on the slide here that you could give. It's not terribly exciting. Suppose that d and y are independent coin flips, and x is a bell that rings if you get at least one heads. So the coin flips are independent, but conditional on x, they are no longer independent. And if you don't believe me, you can do a quick probability calculation. So here is the collider rule. If there is only one path between d and y, and x is their common effect, then d is independent of y, but it's no longer independent of y after we condition on x. So just to recap, we've so far looked at these three special DAGs, and we've talked about the sort of pattern of dependence and independence that they have when you either do or do not condition on x. And the reason we need to learn these is because each of them has a different flavor. So in this example, quite different from the previous two, we start off with independence, and then after conditioning, we then have dependence. The previous examples had the reverse behavior. So you may want to go back at this stage and just review the other two for purposes of comparison. All right. The example with the bell and the coins isn't really that interesting, so here's maybe a slightly more entertaining example. Have you ever wondered why brilliant researchers are often lousy teachers? Well, what I have done here is I have generated a whole bunch of fake professors, and I have generated these professors using a standard normal distribution for each of two quality scores, a teaching score and a research score. So you can see that these points are just kind of scattered randomly along the box. There's no correlation between them. I've generated teaching and researching ability as just completely independent normal random variables. So on the left-hand side, I'm going to show the distribution between research and teaching ability in the population at large. So we're just going to imagine that everybody out there in the population has some ability to do research, some ability to do teaching. Suppose they're uncorrelated. I have no idea if in reality they are, but just suppose that's the case. That means that there's really no regression slope between research and teaching. Well, in the picture, sort of slightly positive, but that's not statistically significant. All right, how about on the right-hand side? Well, what I'm going to do on the right-hand side is I'm now going to imagine that some people can become professors. Not everyone can become a professor, of course. If they're thinking about hiring you to be a professor, they would like you to be good at teaching, and they would like you to be good at research, because those are two key things that you do in your job. Of course, if you're really good at research, then maybe they will tolerate you being not quite so good at teaching. And if you're really good at teaching, then maybe they will tolerate you being not quite so good in research. You do need to have a certain level of quality in both, but let's imagine that they can kind of trade off against each other at least somewhat, which I think is quite plausible. So what I'm going to do now is I'm going to imagine that you become a professor if the sum of your research and teaching scores is in the top 10 percentile, top 10th percentile of the sum of research and teaching scores for everybody in the population. So to indicate this, in the right-hand diagram, I have colored in all the professors in blue, and I have colored in all the non-professors in this sort of reddish color. So what do we see? Well, even though there is no relationship between teaching and research in the population, when I condition on being a professor, suddenly there is a negative relationship between teaching and research abilities. Why is that? Well, that's because being a professor is a collider. And so here we have an example in which there's no dependence before we condition on X, and there is dependence after we condition on X. In fact, if you think hard, you can find many, many, many examples of collider bias out in the wild. It's a little bit more exotic than perhaps some of the others, but it's no less important. Well, after that fun detour, it's time for our final special DAG, and that is called the descendant. So on the right-hand side, we have a diagram, we have a DAG that shows the descendant. So in this DAG, Z is a descendant of the collider X. So here's the thing about the descendant. The descendant can be a descendant of anything. It can be a descendant of a collider. It could be a descendant of the middle node in a pipe. It could be the descendant of the middle node in a fork. So in some sense, the descendant is like an add-on. It's a thing that you add on to each, or I should say any, of the preceding three special DAGs. So you could go back to any of those three DAGs, right? The pipe, the fork, and the collider, and you could add an arrow coming from X out into Z, and then you would get three possible versions of the descendant. Here I'm just showing you one version of the descendant, a descendant that comes out of an X that is in fact itself a collider. But the reason I only show you one is because actually the rule for descendants is pretty simple. It's that conditioning on a descendant, Z, of X, has the effect of partially conditioning on X itself. So now what that means in practical terms depends on what X is. So it has the same effect as partially conditioning on X itself. So to find the effect of conditioning on Z, you need to know what the effect of conditioning on X would be. In this diagram, X is a collider. So conditioning on X would take us from a situation where D and Y are independent to one where they're dependent. And since Z is a descendant of X, conditioning on Z will have part of the same effect as conditioning on X itself. So it will induce partial dependence between D and Y. So again, what this means, what the descendant does, depends on the situation. Here we have a collider, but it could just as well have been the middle node in a pipe or a fork. If that were the case, then adjusting for Z would partially block the path from D to Y. So at this point, you may want to go back and just remind yourself about the other three DAGs we've seen so that you can see how the descendant interacts with each of them. All right, now it's your chance to practice what you've learned. I would like you to find all the examples of the four basic DAGs in this birth weight DAG that we introduced earlier in the lecture. I count two forks, X, U, Y, and X, D, Y. I count two pipes, D, X, Y, U, X, Y. I see two colliders. X is a collider because it has an arrow coming into it from D and U. Y is also a collider because it has an arrow coming into it from D and U. I also see a descendant. Y is a descendant of the collider DXU. All right, so there's been a lot of buildup in this lecture, but now we're finally ready to start seeing the payoff. So let's take a bit of a bird's eye view here. So we've got these four basic DAGs: fork, pipe, collider, descendant. What we need to know about them is what happens when we condition on X. Now, x is a label. I just want to be clear. It doesn't matter if we call the node x. I'm calling it x because I'm trying to evoke the selection on observables terminology. So in the fork, x is in between d and y with arrows coming out of arrows coming out of x into both d and y. That path, the one between d and y, starts out open, but we can close the path by conditioning on the confounder. So we would like to close that path if we're interested in understanding the causal effect of d on y, because that's a spurious causal path. It's true that there's a path between d and y in the fork, but it's not causal because there's not an arrow from d into y that follows the one-way signs. With the pipe, on the other hand, the path from d into y is not a spurious path. It's a causal path. It goes from d into x, x into y. It follows the one-way signs. This path starts out open. If we were to condition on the mediator x, that would block the path. So here we don't want to condition on x. If we're interested in learning the causal effect of d on y, don't condition on x. In the collider, we have an arrow going from d into x and y into x that starts off blocked. A collider blocks the path by default. If we conditioned on it, we would open the path. That would be bad because if that path is open between d and y, it's actually not a causal path because it doesn't actually have an arrow coming out of d into y. So finally, we have the descendant. Conditioning on a descendant of a confounder or a mediator is partially going to block the open path. Conditioning on the descendant of a collider is going to partially open the blocked path. Okay, and now we're finally ready to state the backdoor criterion. So we're going to use what we know about the 4 basic DAGs to find a way of blocking all of the backdoor paths between d and y in our big DAG, the one that has lots of different ingredients. This will allow us to obtain the interventional distribution from observational data. And here it is. So recall what a backdoor path is. That's a non-causal path between d and y. It's a path between d and y that starts with an edge pointing into d. A set of nodes x blocks a path if and only if this path contains a pipe or fork whose middle node is in x, or a collider that is not in x and has no descendants in x. So let me say that again. A set of nodes x blocks a path p if and only if this path p contains either a pipe or fork whose middle node is inside of x, so inside of that set of nodes, or a collider that is not in x and has no descendants in x. So this is just an application of what we learned about each of those basic DAGs to the idea of a much larger DAG. So what the backdoor criterion says is that a set of nodes x satisfies the backdoor criterion relative to dy if no node in x is a descendant of d, and x blocks every backdoor path between d and y. So that is the name of the game. We want to try to find a set of nodes x such that we can block all these backdoor paths, and we're not going to condition on these descendants of d. Okay, that's very formal. That's very abstract. Let me now give you a simpler way to do it. So here's a less formal way of explaining the backdoor criterion. The first thing you've got to do is list all the paths that connect the treatment and the outcome. Then you need to check which of them are open. A path is open unless it contains a collider. Then we need to check which of those paths are backdoor paths. So a backdoor path is a path that has an arrow pointing at D inside of it. If there aren't any backdoor paths, then you're done. Congratulations, you don't have to do anything. If not, if there are some open backdoor paths, then you've got to look for nodes that you can condition on to block the remaining open backdoor paths without opening any new ones. And of course, the trick here is that we can only condition on observed variables. In a given DAG, there may be no way to satisfy the backdoor criterion. If so, that's life. That's a pity. It's just that what we observe can't allow us to carry out a successful selection on observable strategy. but there may also be multiple ways to do it. And now we're finally ready for the big result, which is the backdoor theorem. Turns out this is just exactly the same thing as selection on observables by regression adjustment. So if x satisfies the backdoor criterion relative to d and y, then the probability of y given do d, so that's the interventional distribution, y equals y given do d equals d, is the same thing as, now notice what we're doing here, we're doing basically iterated expectations, or if you like law of total probability, we're summing over all x. The probability that y equals little y given d is d and x is x multiplied by the probability that x is equal to little x. So the thing on the left-hand side is an interventional distribution, and the thing on the right-hand side is an observational distribution. So this shows us how to go from the causal thing on the left, which remember is the thing that we imagine obtaining by cutting some links out of the DAG, by cutting the arrows pointing into D out. We can obtain that thing from the observational distribution on the right-hand side, and the formula is just exactly the same as this regression adjustment. If, in fact, x is empty, then we don't have to condition on anything at all. And here's the big reveal. If x satisfies the backdoor criterion relative to d and y, then this means that the potential outcomes yd are independent of the treatment variable conditional on x for all values of d. So that brings us right back to our potential outcomes version of the world. So this DAG stuff is not, in some sense, incompatible with what we've talking about before. It's a different way of thinking about it. So these counterfactuals, yd, are nothing more than our potential outcomes, which we talked about at the beginning of the lecture. So, so the backdoor criterion implies a selection on observables assumption for d given x. And the formula that we need to use is just nothing more than regression adjustment. All right, so what would we need to adjust for to learn the effect of each of these interventions? First of all, the causal effect of d on y. Second of all, the causal effect of x on y. And third of all, the causal effect of z on y. Well, let's go through each of these in sequence. For the causal effect of d on y, there are in fact two backdoor paths. So if we take a look at this one from between d and x and y, we see that there's an arrow coming into d. It starts there, and you can trace that back to x and into y. So that's one backdoor path. Let's look at that backdoor path, d to x to y. Well, that is a fork, and the middle node in that fork is x, so we could close that path by conditioning on x. Okay, what is the other backdoor path? Well, this one is d to x to z to y. All right, so let's take a look at this. How could we do this? So here the middle node in a pipe is x. So there is a pipe in that path. So again, we don't have to look at the entire path, d to x to z to y. We can just look at d to x to z. That little piece of it is a pipe. So d, x, z is a pipe, and x is the middle node. So this starts out open, and if we condition on x, we close it. So what we've just seen is that if we adjust for x, we're going to block both of those two backdoor paths, and those are the only ones that there are. So in this particular DAG, if you wanted to learn the causal effect of d on y, you'd want to control for x. You'd want to adjust for x, and that would give you the right answer. You could go back and do regression adjustment, and everything would work just fine. So how about the causal effect of x on y? All right, so here, the only backdoor path is between x and z and y. So again, that's a backdoor path because there's an arrow coming into x. So let's have a look at this. In this path, z is the middle node in a fork. So if we adjust for z, we will block this path. So if you want to learn the causal effect of x on y, then you want to condition on z. You do not, however, want to condition on d. And we can sort of see why. If you look at x, you can see that there are two paths, two causal paths from x to y. There's one that goes directly from x into y. There's another one that goes from x into d, and then d into y. So the total causal effect of x actually encompasses both of those two paths. Causal influence flows to y directly from x, and also indirectly through d. So if we were to try to adjust for d, what we would end up doing is actually blocking the portion of the causal effect of x that flows through d into y. And that's not what we'd want if we want to learn the causal effect of x on y. We want to take into account all the different ways that x influences y that are valid causal paths. So the only one we want to get rid of, the only one we want to eliminate, is the backdoor path. All right, what about the effect of z on y? Well, there aren't any arrows pointing into z, so there are no backdoor paths. We wouldn't have to adjust for anything. And finally, we're ready to give a potential answer to this interesting question about the birth weight paradox, namely that among low birth weight infants, maternal smoking was associated with lower infant mortality. And just to refresh your memory, here y was mortality, x was birth weight, d was maternal smoking, and u was lots of unobserved things, among them malnutrition and birth defects. The idea was that these could be common causes of both x and y, common causes of both birth weight and infant mortality. All right, so should we control for birth weight x if we want to learn the causal effect of d on y? Well, if we believe this model, then in fact, x is a bad control. First of all, we cannot adjust for u because u is unobserved. So we're just sort of out of luck there. U is lurking in the background. There's nothing we can do about it. Now, there are actually, in this particular DAG, the way we drew it with the assumptions we made, there are actually no arrows pointing into D. That means that there are no backdoor paths. And if you look at x, what kind of a variable is x? Well, x is actually a collider. So the path dxu has x in the middle as a collider because there are arrows coming into x from u and from d. So that means that conditioning on x creates this basically spurious dependence between u and d. And that is the reason, potentially, for the birth weight paradox. So here's a way to put that into words. Low birth weight infants whose mothers did not smoke, so think about this, you're born low birth weight and your mother did not smoke, well then what must be the case? Something else must have gone wrong. So you must have had an unfavorable value of u. Maybe there was malnutrition, maybe there was a birth defect. Okay, so what happens? Well, that makes it appear as though smoking has health benefits, which clearly doesn't make sense if we think about that in terms of the science involved. But we can see here that it's just purely a result of conditioning on this collider x. And when you begin to think about the world in this DAG sort of framework, you're going to start to see more and more examples of these peculiar results. And I think in particular, the collider bias is a really interesting one to keep an eye peeled for. So that is the end of this lecture on DAGs. I hope that it has at least convinced you that selection on observables is much less straightforward than you might have thought it was. But the good news is that, in fact, there is a framework that allows us, if we're willing to write down our assumptions, to determine exactly which variables we should and should not control for when we're trying to do causal inference from observational data.